Good morning, everyone, and welcome back to the WST 20 Minutes Time Domain Talks. It's a pleasure to introduce our first speaker of the year, Antonino Nunnari, a third-year PhD student in astronomy, astrophysics, and space science at the Observatory of Rome. His research focuses on variable stars, combining optical and near-infrared spectroscopy to study stellar parameters and chemical abundances with particular emphasis on classical Cepheids and galactic abundance gradients. Today, he will speak about classical Cepheids as time domain spectroscopic targets for WST. Dear Antonino, thank you for accepting our invitation. The floor is yours.
Thank you, Giulia. Thank you, Fateme, for inviting me to this meeting. Okay, you already say everything about a brief introduction to me. So I add just that I'm working together with Giuliano Fiorentino, Valentina Dorazzi, Giuseppe Bono. And so the organizers asked me to present my work and to link this work with future possible projects that can be carried out using WST. So I'm going to introduce the main results from this work that focused on chemical gradients of the thin disk using classical Cepheids. And then I will, at the end of the presentation, link this with the WST. So the main character of this presentation are classical Cepheids. You probably know everything about that, but let me go very fast into this. Classical Cepheids are, as variable stars, precise distance indicators, thanks to period luminosity relation. So simplifying, you know exactly where they are. And they show very high regular periods ranging from days to months, thanks to the period age relation. This time, you know exactly the individual ages. And as central helium burning stars and intermediate mass stars, they are young, with ages within a few hundred mega years. And this means that they are ideal young stellar tracers, ideal for tracing the young components of a stellar population, in particular, the thin disk. This is an example of how good they are for tracing the thin disk. A study from the Mullen collaborators. You can see on the left figure the face-on view of the thin disk. Each point is a Cepheids. In this study, Cepheids have been used for tracing the spiral arms. On the right panel, you can see the edge-on view. Again, the Cepheids have been used for tracing the so-called galactic warp. That is a distortion that occurs in the other part of the disk. This is another nice plot, this time from Chen and collaborators, about the galactic warp. And I will go back to this point later. Now, let's focus on the main goal of our study, the chemical gradients of the thin disk. Why chemical gradients? Well, in a sentence, chemical gradients are one of the few observables that we have for constraining the chemodynamical models of the Milky Way. For example, if you see a negative gradient, this is in agreement with a theoretical framework of an inside-out scenario in which you formed first the inner part of the thin disk, and then in a later moment, you form the outer part. Well, we want to reconstruct the chemical gradients using, of course, high-resolution spectroscopy for getting the abundances of a lot of elements, alpha, iron peak, neutron capture, light elements, in order to have an entire view of each channel of production and to build the chemical enrichment history of the thin disk. Now, another important point of this study, well, most of the study in literature about chemical gradients using Cepheids rely on local thermal equilibrium models. But these theoretical prediction and observational bias and observational evidences tell us that this can be affected by systematic errors, in particular when transitioning from dwarf stars to giant stars. And these corrections are element and line dependent. So we can use a non-local thermal equilibrium approach, since now we have the chance, thanks to new grids from Martian Collaborators 2020. Just to see an effect of the non-local thermal equilibrium departures, in this figure on the left, you can see the delta of the atmospheric parameters. Delta means non-LTE minus LTE. And you can see how these plots are as a function of the metallicity. If you go toward the lower metallicity, this delta becomes higher, becomes stronger. On the right panels, you can see the delta of the abundances, in this case, aluminum, sodium, manganese, and magnesium. And the giant stars are depicted with this dotted line. Again, you can see how these differences are very important. Now, within this framework, I'm going to introduce our dataset. So this dataset has been collected by our group and analyzed in the Silvan Collaborators 2023, a dataset of 1,285 high-resolution optical spectra for 379 classical Cepheids. And on the left panel, there is the distribution of these Cepheids across the thin disk. We cover from 4 kiloparsec up to about 29 kiloparsec. We also added other high-resolution spectra, reaching 1351 high-resolution spectra for a total of 400 Cepheids. For most of them, we have high signal-to-noise ratio in order to take down the uncertainties on the estimated parameters. Okay, commercial break. This presentation is sponsored by PySME. This is the code that we employed for making our measurements, basically, to perform our spectral synthesis. So if you are interested in, you can look to these links and references that I put into this slide. Okay, first results. Here you can see the delta of the atmospheric parameters, again, non-LT minus LT, as a function of the respective parameter. And we compared our results with what we have in literature, in particular, the study from Rupti et al. 2013, in which they analyzed the effects of non-LTE departures. What we found is that the behavior as a function of the metallicity, of temperature, of gravity, and of the metallicity itself is consistent. Okay, we found an offset of about 0.20, 0.30 kilometers per second in microturbulence. But also, if you see to the single Cepheids, so the single values, you also find that the variations in temperature can reach 400, 500 Kelvin. In gravity, you can also have 1 dex of difference, and so on. And these support the fact that the non-local thermal equilibrium departures are not negligible. We compared our metallicity with other studies. In particular, on the left, you can see a comparison with LAC 18 and with Trentin 24. On the right, you can see the comparison of the metallicity with the Silvan collaborators. So what we can see in these comparisons is that trends and offset can appear. And this is something expected because we are using different spectral analysis, different line list. What we found is that these trends are not primarily related to non-local thermal equilibrium effects. But the main reason behind these trends and these offsets rely on the different spectral analysis and line list. Now, about the iron gradient, one of the first attempts to reconstruct the chemical gradient, the iron gradient, using a large sample of classical Cepheids. I think someone is speaking.
Did you stay in Barcelona or you went somewhere?
Went to Barcelona.
Okay, wow.
Some of my family.
Oh, okay, I can go. Was this study from Genovali and collaborators? They covered the gradient until from 4 kiloparsec up to 18 kiloparsec, and they found this negative slope. Then there was Luck and collaborators 2018. They go to 24 kiloparsec, and even with large uncertainties, they found for the first time a flattening using Cepheids. Flattening that is confirmed by the Silva and collaborators, where the authors covered up to 29 kiloparsec using a logarithmic analytical function for fitting the data. Then we also have 2024 as the study from Trentin, in which this flattening is not found. What we understand from this is that the iron gradient is there, the negative slope is there, but still we have a lot of uncertainties about the global shape, the exact analytical function that fit the iron gradient, in particular in the inner and the outer part of the disk. Okay, our results about the non-NLTE iron gradient is this one here in gray. I also overplotted in orange open clusters from Occam, the study from Otto and collaborators 2025. Now, within these large statistics, we employed 3 different fitting functions. So linear, logarithmic, and a bilinear model. What we found is that, using also the AIC score, is that the logarithmic function is the one that works the best. And the second place goes to the bilinear model, while the linear one is the worst among these 3. We also employed the Gaussian process regression in order to not be affected by any analytical function, since this is a non-parameterized way to fitting your data. And we can see from the GPR that there are 2 main features that are very interesting, according to me. The first one, around 15-16 kiloparsec, you can see a change of slope, so a flattening that occurs in the outer part. And the other one is at around 7-8 kiloparsec, so around the solar circle, where you can see such a shoulder around here. Okay, we compared these results with literature. So you can see top left panel, linear fitting functions comparison. On the right, a comparison with Da Silva. This is the only one that uses a logarithmic function. And on the bottom, a comparison of the GPR and the other linear functions that are available in literature. In particular, we can focus on the logarithmic comparison because we found that our slope is steeper than the one of Da Silva. Now, if you think about the fact that we use non-LTE while they use LTE, you may expect that our gradient is shallower. But as I mentioned before, the main reason behind this difference is to adjust to the different line lists and to the different spectral synthesis used. as I will show you later, the non-NLTE, as expected, will flatten the profile. Just another comment on the bottom figure here. The comparison of the GPR tells us that there is such an agreement in the inner part of the disk, while in the other part, where we are trying to, let's say, reconstruct better the gradient, since there were like missing statistics that we are now trying to fix. One thing about the fact that the GPR and the log profile actually are very consistent with uncertainties each other. And so this is an interesting point. About the other gradients, well, in literature, what we have is that we are limited to around 18 kiloparsec, and most of the studies rely on the LTE assumption, okay? We are providing the chemical gradients for these elements here. There are those for which we have the non-local thermal equilibrium grids from a Martian collaborators, so magnesium, silicon, titanium, calcium, oxygen, sulfur, sodium, aluminum, copper, and manganese. And for all of these elements, we made the same statistical analysis that we made for the iron. I will go for one of them for a matter of time, of course. And so, first of all, the three analytical functions that we used and the statistical tools that we use tell us that, again, the logarithmic profile is the one that works better. And only for magnesium, we found that the bilinear model can be better, but the problem is that the position of the knee is at around 15 kiloparsec. That is in contrast with all the other gradients. And also, if you believe that the bilinear model is your model, you should also explain from a theoretical point of view the presence of a discontinuity. Now, we also provided the GPR for all these elements. Again, we found a change of slope or a flattening that occurs in the outer part. And for many elements, we also found this kind of shoulder that we observed also for iron. We provided the chemical ratio for all the elements, and for most of them, this ratio remained constant across the entire disk, so up to 29 kiloparsec. And this is an interesting feature, since this means that every element follows the iron, and this means that you can use all elements as a gas, as a diagnostic for the gas distribution. We provide the chemical planes, so X over iron as a function of the iron, and these planes are crucial for investigating the star formation rate, for the initial mass function, and the chemical properties of your stellar population. We made a comparison with the literature, and what we found is a general consistency in the inner part of the disk, and as I mentioned before, better constraining of the gradients in the outer part. Last thing, because I think I'm going out of time, is this one here. So this is the abundance as a function of the logarithmic of the period. As I mentioned before, thanks to period-age relation, we know the individual ages of Cepheids. In this plot, on the right, you will have the youngest Cepheids. On the left, you will have the oldest Cepheids. And what we found is a slightly positive trend for every element. or since there is an higher dispersion, that at the shorter periods, so all the Cepheids show a higher dispersion. And this is a feature that we are going to analyze better, hopefully in a forthcoming paper. Now, this is another result from our study. So if you think our modeling of by using a logarithmic fitting function, we used the non-LTE abundances and the LTE abundances, and we compared the slopes of the logarithmic functions. What we found is that the non-LTE slopes are flatter, as I mentioned you before, and also there is a slight improvement in the accuracy of this relation. I will skip this because this is just to state that we also investigated the kinematic properties in order to say that our targets have thin disk orbits, and we also find a trend in this plane, height as a function of the galactocentric radius that is addressed to the galactic warp, as I introduced before. And this is a recap. So essentially, the main results from this study is that the flattening we found the flattening in agreement with the Sylvan collaborators, and we are also providing, let's say, the non-LTE effects on the atmospheric parameters and on the abundances. And this is the first time for Cepheids. So I think that this can be very interesting, in particular for the future, in which we are going also to the near-infrared. I also am using apogee spectra and there is spectra in order to build a similar analysis also to the near-infrared. This is work in progress. So if you're interested in this, stay tuned. And now, last slide, and then I finished. Cepheids and the link with WST. So one of the main issues that we found in our analysis is that when you use variable stars, in this case classical Cepheids, it's hard to have calibrating stars where you know exactly the atmospheric parameters and abundances. In these figures, you can see different plots. So in this case, we have magnitude, radial velocity, and atmospheric parameters for a Cepheid, Zeta Gemini. As a function of the phase, we are covering the entire pulsation cycle for this star. But this is one of a few cases, because usually this is what we have if we are lucky. Just few points across the pulsation cycle. I think that with WST, we will have the chance to get the individual spectra, and we can cover the pulsation cycle. This will help to investigate the atmospheric parameters variations, the line profile variations, and we can build atmospheric parameter templates. This figure comes from Da Silva 2022, using 20 calibrating Cepheids. And within this, they were able to find 4 templates according to the period of the stars. So in this way, one can investigate, let's say, the pulsation models that are behind the theoretical models behind the pulsation itself. From the observational point of view, this will help us to measure the chemical abundances. So if you have calibrating Cepheids, you can better constrain atmospheric parameters. And this will be crucial for the near infrared, where it's very hard to have lines that are sensitive to the atmospheric parameters. So I think that there are many ways to use the individual spectra from WST into this possible science case. And that's all. I thank you for your attention, and I'm open to your questions.
Thank you very much, Antonino, for sharing your work with us. It's now time to open the floor for questions and comments. I will start, and okay, there is Laurent before. Okay, Laurent.
Yes. Thank you for your presentation. I have several questions. So related to Gaia, we have in the data release 3 an estimation of the metallicity from the light curve, as you probably know. And is there any correlation with the metallicity you are finding through spectroscopy? So is it good or just okay? And then there is another question about the Milky Way formation. So in a way, does your model confirm the inside-out formation? And you don't speak about migration. And could the migration explain a bit the shoulder in one of the plots you have? And also, you could maybe use, that's just an idea I was thinking, maybe looking at a certain radius, not only the mean, but the dispersion, the standard deviation you have. And it could be maybe trace or a measure of the migration effect. What do you think about these 2 points?
So for the first question about the metallicities from Gaia, I didn't use the Gaia metallicity because most of the sample, for most of the sample, we had other spectroscopic high resolution spectroscopy estimates that were from Da Silva and collaborators. And also we compared our metallicity with other studies that used high resolution spectroscopy as LAC, as Trentin. So using common Cepheids, we were able to make these comparisons and see, as I show in a slide here, exactly this one here, how these estimates talk to each other. For the second questions about the radial migration, well, the point here is that Cepheids are very young, so essentially they don't have time to go in another location of the disk.
Yeah, thank you. That's
welcome.
But anyway, I think that you can include the Gaia in your future papers for comparison.
Yeah, of course.
And I have a question about the statistical tools you use to confirm that finally the logarithmic profile is the best.
Yep.
Which kind of statistical tool?
Yeah, okay. So yeah, we use a Bayesian approach for getting these fits, using also the uncertainties in x-axis and y-axis. The statistical tool that we used was the AAC score, which is telling you which model is the best according the complexity of the model, so the number of the degree of freedom that you have, and also the probability of your work, so the maximized likelihood. So considering these 2 things, you have your score, and from our code, we found that the logarithmic one has the lowest AAC score.
Okay. Another question, I'm very interested in the slide that you showed about age effects. Can you tell us something more this future work? if you have something
Yeah,
just
so the idea is to cover, let's say, to enlarge the sample in order to see if there is any pattern in age. So the advantage of using Cepheids is that within period you can estimate the age. From these plots, we have a hint about the fact that that the youngest Cepheids prefer to stay in the inner part of the disk as a global on average, let's say. While in the other part of the disk, we have a larger dispersion. So the oldest Cepheids are formed in the outer part. So this is, of course, an introduction. I think that if we enlarge the sample and we are doing this, we can have a better view and also compare this kind of map with the abundance that we have in order to see if there is some relation, some link.
Okay, thank you. Very interesting. Other questions and comments? Okay. I think that we can wrap up the session here. Thank you very much, Antonino,
Thank you.
and, for all of you, and a very nice day, everyone. Bye.
Bye-bye, thank you.
Bye, thank you.
Thank you. Bye bye.